Welcome back, Physics 30. So this is the FM1.9 section, Kinematics of Uniform Circular Motion. So here we'll look at determine the characteristics, velocity, period, distance traveled, and acceleration of uniform circular motion, or in short, it's referred to as UCM. So uniform circular motion is motion in a circle of constant radius and constant speed. Now, as we notice, there will be a difference here between velocity and speed, but if we're going around at so many meters per second, that is the part that's staying constant. And of course, the radius is staying constant as well. So to determine the speed of an object in uniform circular motion, of course, speed we know is distance over time. And of course, the distance traveled here in circular motion is equal to the circumference of the circle. And of course, we know from earlier math classes, 2 pi d, pi times the diameter, or of course the diameter is 2 times r. So of course, sometimes it's referred to as 2 pi r. So distance traveled is 2 pi r. And the time is big T. Now big T, if you recall from physical science, means period. It's the time it takes for an object to travel once around the circle. So sometimes referred to as period. And of course the distance traveled is 2 pi r. So distance over time, 2 pi r over T. The time it takes to make one complete circle, because that is a circumference distance, right? So distance to go around once, time to go around once. That'll give us what the speed is. Circular motion is often described in terms of frequency, and which is the number of cycles per second, or in our case, complete revs per second. And period, which is the reciprocal of that, how many seconds it takes to make one rev. And if you remember from Physical Science 20, these are the relationship between frequency and period. So what we could do is copy out, so over here, period, maybe we'll just state that. So period can be, and it's of course symbolized as big T, and it is the number of seconds over number of revs. And then frequency symbolized by little f. If you go on and take more physics classes, you'll see that it's symbolized by that, the Greek symbol nu. Number of revs per number of seconds. Okay, so that's how we do that. Now, in these cases, the only cases that we're going to be talking about is horizontal circles. So in the plane equivalent to the ground. When we look at a situation like a Ferris wheel, for example, it's in the vertical plane. We're not going to look at those examples. So we're going to keep it easier and just look at horizontal to the ground. All right, so let's look at this first example. So the wheel of a car has a radius of 0.29 meters and is being rotated at 830 revs per minute on a tire balancing machine. Determine the speed at which the outer edge, i.e., which is 0.29 meters from the center, is moving. So we're looking for speed. So of course speed in a circular motion is 2 pi r over t. So we know the radius, but we don't know the t. We have some information here about the frequency, but again, frequency, revs per second we need, and here we have revs per minute. So the first thing we're going to have to do is change revs per minute to revs per second. And of course, revs per 1 minute, and of course we know that 1 minute is 60 seconds. So if we arrange it like this, we know that minutes will cancel, and if I was to stop right now, of course that is revs per second, which is what I want. So 830 divided by 60, we get around 13.83 repeating revs per second, but of course I need t. So first of all, let's put this as f, right? number of revs per number of seconds, so I had to start off with revs per minute, change it to revs per second. So looking for t, I know that it's 1 over frequency. And we did these types of questions in Physical Science 20. So that equals 0.072 seconds. Okay, so now we're in the position where we can figure out speed, 2 pi r over t. So 2 times pi times the radius, which is 0.29 meters up there, and divided by our period, the time it takes to make 1 complete cycle. So we're going to have meters per second as a unit, and I think that works out to be, to 2 sig figs, 25 meters per second. Alright, so those are kind of some of the new relationships there, looking in a circle. So if we look at the next page, now we talked about speed, right? So speed is equal to distance over time. Now if we look at velocity, velocity of course is displacement over time, and it has a direction. So velocity, so if we look at instantaneous velocity, it's always tangent to the circle. So if we're spinning around here clockwise, the velocity right here would be equivalent to this. The velocity over here would be equivalent to this. So we could see here in all of these, same speed, but different direction. So we have, so the speed is the same, but velocity is changing. Now it's not the magnitude that's changing. Magnitude, the size of this velocity is this, the magnitude is the same, but direction is changing. So it'd be like saying if you're driving in a circle with your car going 20 kilometers per hour, you're staying at 20 kilometers per hour, so the speed is the same, or the magnitude of velocity the same, but the direction is constantly changing. So speed is the same, but velocity is changing. And since velocity is changing, we must have an acceleration. Now the acceleration is just simply changing direction. Look at the change in velocity and the limit that the time interval becomes infinitesimally small. We see that the acceleration, or sometimes it's referred to as radial or circular acceleration, is equal to v squared over r. And if we take a look at where that formula comes from, we can take a look at what's happening around the circle here. So we have a certain radius, right? And if we're looking at 2 points on the radius, let's say points A and B, okay? So we have a triangle here. We have R and R, and this change in length here joining up these 2 points. So that is a kind of a position triangle that we'd have here. We also have a triangle here involving V1 and V2. Now we know that if we're talking about speed, they're equal, but if I take V1 and V2, V1 plus the change that happens gives us the resultant V2. Okay, so what happens here is we can make a triangle out of V1 plus the change that happens makes me go to V2. So I just took these vectors, placed them here. Now I placed them tail to tail because the change here represents what I'm adding on to V1. So if you take a look here, add V1 to each side, and I get this. So that's what I'm doing here. So V2 you can think of as the resultant, and then if I take my V1 plus the change that happens, I get that. Now, these are 2 similar triangles, so their ratio should be the same. So this change in V over one of these V's is equal to the change in L over R. So small side over big side equals small side over big side. They are in the same proportion. And if I take a look here, if I solve for delta V, I get, let's see, time multiply each side by V, I get this. Okay. And I know that acceleration is change in velocity over change in time, right? That's what acceleration is. And I could put my vectors here too. Now, if I can represent my change in v as this, so I can think of it as, okay, so it's delta v over t, but my delta v can be represented as this over r. And of course, so yeah, so all I did is I represented this as that, right? Because they're equal. And then they have delta t on the bottom. And here's the interesting part. A change in length over change in time. Change in length over change in time. Well, that's a velocity too. So you can see what I end up here. I end up with v times v over r squared. So v squared over r squared. So that's how we get that equation, really. Why there's a v squared. Because with radial acceleration, we have those two similar triangles that we can relate, and it turns out to be that. All right, I think we'll stop the video there, and we'll come back and do the rest of this section.